This lecture is all about principal component analysis. It's the first of several lectures that we're going to have on this topic. And it's going to be a sort of a foundational topic for us in the sense that when we learn other techniques later on, we're going to sometimes tinker with them a little bit and understand how do they relate to principal component analysis? Or how is it that you can tinker a little bit with principal component analysis and get this other method? Or something like that. So it's going to be really foundational for us. And so we're going to spend a lot of time trying to understand its inner workings and details, and it should pay off in the long run throughout the class. This lecture really is all about kind of a motivational or intuition building aspect of this. So we're going to draw some sort of pictures and cartoons and sketches and try and kind of get an understanding of what exactly is the point of principal component analysis and what do we hope to gain and hope to get out of it. In the next lecture after this, we'll start to lay down some of the explicit mathematical details and see how do you actually go about doing this. And we won't really code these mathematical details up from scratch, but instead, in the lecture following that one, we'll use some kind of prepared algorithms in our preferred programming language for the class, R. We'll use those and try them out on some example data sets and some example problems. But so that's just the first few of these lectures, and it really is the case that principal component analysis is an important analysis tool, and it shows up in other areas of science where it's the same techniques are used, but it comes with a sort of a different language that goes along with it, and you don't use that same terminology. But and in this lecture, at the end of it, I'll give a couple of examples like that where you can see similar techniques used in other subjects. All right, let's just dig in. This is called Principal Component Analysis, or PCA, and it's a kind of a powerful technique that's used for multivariate data analysis. And so I'm just going to start off with some vague, rough descriptors of what we're doing, and then we'll work through a couple of specific examples. So this tool, PCA, is used for the analysis of real or numerical multivariate data. To use it for something that's not numerical, so say like I think depending on your educational background, you might call it a factor, or you might call it a categorical feature or something like that, then it doesn't work so well for that. There may be other related methods, but this, as I'm describing, it doesn't work quite right for it. So used for analysis my writing, it's funny. Used for analysis of real, or if you don't like the word real, like in the mathematical sense, numerical data. So, for example, it's not so useful if your data consists of which of the following is your mood: happy, hungry, sleepy. Like, those are not really numerical pieces of information. It really is one of the main topics, as I've said, so it maybe is the main topic for this module. One of the main MT5758 topics. I expect many of you, maybe even all of you, will try to use it in some way, not even just in this class, but in others. It'll be useful for your projects and so on. All right, and so let's try to write out what are our kind of goals when we introduce this thing. All right, so the overall goal of PCA is that the construction is that you imagine you've been given a collection of data that you're supposed to analyze, and you store the data in this matrix X, like we've been talking about, and it has n rows and p columns for each feature as a column, and so on, the usual way we've been describing it. The goal of PCA is to somehow reduce the dimensionality. So if you were given a problem that had 10 variates, you might want to try to recast that data set in terms of only 2 variates. So that's the idea of reduced dimensionality. If you do that, you want to do it in a way that minimizes information lost. All right, so that's one of the goals. You want to reduce the number of dimensions, or at least you want to have a way to do it. And you want to be able to do it in such a way that the amount of information lost is as small as possible. In the language of statisticians, I don't know if this is so much a goal or rather a descriptor. I guess it's a goal. You want to generate hypotheses. So you use PCA to help you generate hypotheses about the data rather than test the hypotheses. Not test them. Right? So it's really kind of a hypothesis generating tool, an idea factory, if you want. In some sense, you want to prioritize things, and that'll become clear as we go along. Want to order or prioritize. Something, and this will get to. It'll come up as we go. This means that this PCA is called an ordination technique. This is just introducing you to some lingo. Or ordination method. It's not the only such thing that we'll encounter in this module. When we get to multidimensional scaling later, we will. That's another ordination technique. Okay, so that's enough kind of advertising. There's more advertising in the notes. I want to talk straight away about just an example. So we'll just try it and we'll see what goes on. And it's a really simple example. It's so simple you wouldn't really do it, but it's useful to understand. So I want to think about a two-dimensional or a two-feature data set, or bivariate. Two-feature case. Also called 2D for 2 dimensions, right? Okay, so we're going to focus on this one a lot just because it's simple and try to understand what's happening. So, okay, suppose that the setup is, as we've said, you've got this matrix X, right? So this is the data. Let me write this. Right, and it's a collection of elements X, I, J. Sometimes people always insist that the elements of a matrix, usually capital letters are used for matrices, and the elements of matrices are done with lowercase letters. I don't really see the value of that, and I skip it often. Okay, but so let's say specifically that it is an n by 2 matrix. And specifically, let's even name things. Because it'll help us, if the more concrete we make our example, the simpler our lives will be. So let's say that the first column is height. So maybe these are about people or animals or something in centimeters. And the second column is weight or mass in kilograms. Right, and so the matrix X is built out of these 2 columns. If I wanted to, I could just write it as a table. And so there's like, here's X11, and here's X12, and here's X21, and X22, and so on, until we get down to the end. And if there's n rows, we have X, N1, and X, N2, right? So those are the those are the table. That's a table of the elements in the matrix X, heights and weights. Let's say we're interested in understanding the relationship between the height and weight of different animals or people or something like that. And you can represent that on a plot, which you will often do, like this. Oops. Okay, and so let's say this horizontal axis is height. Right, so that's the first column. And the vertical axis is the weight. Right? Now, it makes sense to imagine that for people at least, that these things are sort of correlated. Taller people probably weigh more in general, not always, but in general. And so we'll draw some sort of representative data points on here. Let's say you collected some. Something like that, right? And so each one of these, again, I'm going slow through this because I want to build intuition. I want your intuition to be kind of strong. This is one row. Each point represents one row of the matrix X, right? And so this guy is X, and whatever row he's from, column 1, and X, whatever row he's from, column 2. Right? So that's just that one point, and each other point is like that as well. Now, the idea behind PCA is that we want to represent this data on a kind of different coordinate system, or a different set of axes, not necessarily the ones that you see here. It could actually happen that the ones you choose ultimately are pretty close to the things you had to begin with. That could certainly happen. So this is our task, right? So we want to represent the data on new or better axes. All right. And these are going to be called the principal component axes. PCA stands for Principal Component Analysis, but whatever. Here's another acronym you could use PCA for. All right, and so the idea is we've got the data originally on pairs of height and weight. And we want to somehow transform it so that each row is not a height and a weight, but is some other thing. And we'll call that like principal component 1 and principal component 2. Maybe each of those things, principal component 1 and 2, is maybe somehow built out of height and weight. Like, what is that? Body mass index? I think that's done kind of like that. Anyways, so that's the idea, all right? And let's just make us a drawing. Okay, I'm going to have to reproduce this plot multiple times, so I'm going to copy it. And I'll delete some pieces of it. Oops, I did not want to. Okay, so I'm going to erase some of this notation. These labels. All right, so we've got our data points here in height and weight. And we want to pick a new set of axes, all right? So the very first thing you do, so I'm going to just lay out kind of in its steps here what you do. First step, put the center or origin, the principal component origin, at like the most kind of natural place you might think. I don't know if you know what that might be. If you have some idea, what might be the most natural place? So I'll make this a red star. So you should think about it for a second before I just yammer on with the answer. But so the idea is that the center should be at the following. So it should be at the place of the average height, right? Which is just the x bar 1, It's sometimes used as a notation, but it looks like this, a 1 over n sum I equaling 1 to n of x row I column 1, right? So the average of all the heights. And then similarly, the weight for the center should be the average of the weights. Right, so let's just copy this. And there we go. So this is x bar 2 and x row I column 2, right? Okay, so that's where you put the center, right? So let's just draw that in someplace, right? And this is all sketched, okay? This is not, I did not make a calculation that this is where the star should be. But let's just say it looks plausible to me that it goes there, all right? And then, so what we're going to do, and I'm going to copy this because I'm going to want it again. What we're going to do is we're going to put our principal component axes on here, starting from this origin. So like maybe PC1 is going to go like that. And maybe PC2 is going to look like that. We don't know yet. There's a procedure for deciding where they go, just in the same sense that there's a procedure for deciding where the center is. But so this is the picture, right? We're going to throw down these axes and then describe the data in terms of these new axes. All right. So let's do this again, and I'll just draw PC1. Right. So this is now step 2. Okay, what we want to do is orient PC1 randomly. Principal component 1 axis, or arbitrarily. Just pick any orientation you want. This is not quite how you go about things, but let's just do this and discuss it. So let's say I pick it kind of looking like this. All right, so that's my PC1 axis. The red star is at the place where PC1 is 0, and so on. Right? Now, for each of these green points, I project them down onto the PC1 axis. All right, so that's like step 3. Project. And that word you might not know what that means, and so I'm going to try to clarify it. So project the data onto the PC1 axis. Right? And what that means is the following. So I'm going to copy this again. So I have lots of duplicated pictures here. Sorry, it's going to take up a lot of virtual paper. Okay, so projecting the data onto the PC1 axis means the following, right? You take one of the points, so I'm just going to look at this guy for starters, right? And you draw a line down to the axis, and then you put a point on the axis. But of course, the problem with this is which line do you draw, right? So here's another line that goes from the point down to the axis, so I could put the point there. So what does it mean to project the data onto the axis, right? There's all these different places. Well, what it means is that you draw a line that is perpendicular to the axis that you're headed towards, right? And so that's the location of this particular point, right? So if this point over here, we had labeled this guy, how did we label it, right? X row I column 1. So some particular row I column 2. So that's how it's described in terms of weight and height. But this point here, this brown point, on the PC1 axis, this is just PC1I, right? So it's the number on the PC1 axis that goes along with the 2 coordinates that were in the weight and height dimension. Right? So that's the idea. And you do this for every one of these points. So like this guy, he kind of, well, actually, so this guy here is almost on the axis, so his point is kind of there. I don't know if you can see what I was drawing. I was just looking at this guy here. The next one, like that guy, his point is sort of here, right? So that's a 90-degree angle. This guy's point is sort of here. This guy's point is sort of here, roughly. I'm just sketching this, right? So it looks like this. And so now each one of these points has been put onto the PC1 axis. And you can kind of disembody the PC1 axis from all the other stuff, right? So let's do that. And so I'm going to go over here, and I don't care about any of the previous information, so I'm just throwing it out. Ooh, I'll have to put that guy back. I guess I can leave the red star to remind me that that's the origin, right? And so now the problem just looks like this, right? I've just got one dimension, and the points are somewhere on that one dimension. And so that's reducing the problem down to a single dimension. But of course, we're not really going to stop there. But nevertheless, so now, as I said, we picked the orientation of the PC1 axis just totally arbitrarily. So what do we do next? I think this is step 4, right? So step 3 was to project. Step 4, I want to compute the variance. PC1 variance. Right, so each one of those points has a number, right? So this is like, I don't know, 10, 8, 6. That one's 0. That's not actually a data point if I remember. And like -2, -3, -8, whatever. Each one of those has a number. And so I compute the variance in the usual way, right? So sigma squared, 1 over n. So it's the average. You could do the sample variance if you want. You could put n-1. I don't think it will make any difference here. And then in parentheses here, we got the difference between PC1 for point I, so the number associated with that point, minus the average value of all the PC1 points, which I won't define. I suppose you know how to do that. And so that's the variance, right? So you get some number. Okay, fine. Now, repeat this, all right? Step 5, rinse and repeat, as they say. So step 5, repeat. So reorient. So go back to, where were we here when we just put down our axes, right here, right? Go back to this place here, and instead of laying down PC1 like that, put it in another direction, like that, say. And calculate, and do the projection, and do the variance calculation again, right? So reorient the PC1 axis until you get the largest variance that you have found that is possible, until you find the largest variance. Okay, and here's how it will look. So let me go back here, and I think I can work from this picture. I hope that this isn't like nauseating, watching the pictures go back and forth like this. Okay, and so here's how it will look. So I'm going to erase what I had. Okay, and so the PC1 axis will look something like this. And its origin again is there where the star is. It will point in such a way that you get the largest spread of the data on the arrow, and you probably saw that coming kind of the whole way along. So that's what's meant by finding the location or the orientation that has the largest variation. And so in that sense, PC1 is kind of the most special axis associated with this data. Okay, now, we're not done though. So step 6 is to create another axis, PC2. All right, so put PC2 axis following using the following rules. With these rules, all right? It's kind of broken English. So put the PC2 axis down, not arbitrarily, but following this set of rules. First of all, it has the same center, same origin, has PC1, right? So the center of the data. That's also sometimes called the centroid or the center of mass. That comes from physics. It's the center of mass if each of the data points were a particle, a point particle, and they all had the same mass. Anyways, so the origin is the same as the PC1 origin. And then the other rule, which is pretty important, is that it's perpendicular. Perpendicular to, and the symbol for that, in case you don't know, is like that. That's in parentheses. The parentheses are not part of the symbol. To PC1. Right? Now, that gives us really only... So think about that. So the origin is where the red star is, and it's got to be perpendicular to PC1. That doesn't completely determine where PC2 points, but it does almost, right? You've got only two choices. Either it points up like this, which is perpendicular, or it points down like that, which is perpendicular. There's no other way. There's two ways to be perpendicular to PC1, basically. So you have a little bit of freedom. But so I'll just draw it pointed up. Like that. PC2. All right? Yeah, and so that's our coordinate system. And now we have on this new coordinate system, right, which just looks like this. So there was a lot of freedom for picking PC1. We had to look at those variances and stuff. But for PC2, there wasn't. We just picked one over the other. So now on the PC axes, principal component axes, you can transform, or X is transformed. Into the following, right? So X was what you called your data before, but now I'll just call it Y. And it's equal to a collection of Yij's. And again, I is going to go from 1 to n, and j is going to go from also 1 to 2. And it's going to look like this, right? So it's a big matrix. The first element at the top left is PC1, 1. And this guy is PC2, 1. Right? So those are the principal component locations for the first data point. And so on. Right? So this is PC1, 2, PC2, 2, and then down the line. So on the surface, this doesn't look like we've saved ourselves anything. We did a lot of calculations. We started off with a n by 2 matrix. We, after doing all these calculations, have another n by 2 matrix. But this one is a little better. It's better because we know that the first column is maybe somehow more important than the second. Because if you go back here, right, the second column describes like these distances, which are not as widely dispersed or not as varying as these distances. Well, how do I say them? Wait, did I do that right? Yeah. I got mixed up. The first column describes the location along the PC1 axis, which is here, right? And so we had widely dispersed values, right? So this one, this one, this one here, this one here, this one here, this one here. So it's most spread in that direction. The second column describes, the second column describes the location on this axis. And so there's like here, 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 here. There's less spread there, right? So it's less kind of maybe contains less information or less important information, or I don't know, something like that. So that's the whole idea. So we've made this new coordinate system, PC1 and PC2, and the axes are somehow ordered in terms of usefulness or maybe usefulness. All right. So the columns are ordered. So that's where that ordination technique comes from, right? So they've somehow been put into orders. And so maybe, like, if you only know about doing univariate analysis, say, or you don't want to study more than two features or two descriptors of the data, you can just throw out column 2, maybe. And maybe you have to do that because maybe you're limited in terms of time, deadline is near, or the computational cost is too high if you keep 2 columns or something like that. This is all a little silly for a 2-dimensional case like this, but I hope that this has built up some intuition for the more general case. Okay, so now let's extend this a little bit. So we'll go to the 3D case, and then we'll just talk about general. So we won't do as much detail here. 3D case. All right, so this is where you don't just have height and weight. Maybe you have height and weight and age, say. I don't know. I'm not going to write all the details for this, but and let's suppose here I don't like working on the. I don't know if you can see, but there's like a line break on my fake paper here. Sorry. So let's suppose the data is now like this. So you got these 3 different axes. And I'll name them in the kind of mathy traditional way. This is the x-axis, this is the y-axis, and this is the z-axis. So let's say x and y are, what was the ordering up there? The horizontal axis was height. So this was like x is height, y is weight, and maybe z is age, something like that. And the data points, they exist someplace. Like that, right? And you can say that they exist in a kind of a shape that we call the data cloud. It's the region in the feature space where all the data exists, all right? Okay, now, so here's how we go about the problem, the principal component analysis in the 3-dimensional case. So I'm just going to sketch it a little more quickly this time. Step 1, PC1 starts, or the origin of PC1, so it has its origin at the so-called center again. So that's the point, like x bar, y bar, z bar. So the averages of all the ages, all the heights, width, weights, and ages. You can make your life a lot easier with this if you just center the data to begin with, so that this step is not a part of PCA, that the data already started out centered. It's often a good idea anyways. But anyway, so this is sort of step 1. And then step 2, right? Oh, sorry. I didn't finish describing PC1. There's more to it, right? And has the greatest variance, or it's in the direction, has the direction of largest variation or variance. I'll just put var, right? So in this case, that would mean something that kind of looks like that, right? So PC1 would look something like that. It's in the direction in which there's the most spread of the data, right? But now, so there were 2 other dimensions to this data. So what do we do for those? So okay, step 2, PC2 is perpendicular to PC1, right? Now, just like we had some freedom before in the 2-dimensional case, we'll have some freedom again. And in fact, the freedom is more grand this time. So like, here's a picture, right? So the collection of directions perpendicular to PC1 determines actually a plane. So let's just draw that. So here's the plane. Right, and here's PC1 coming out of it. Right? And then let's just even be fancy. Let's say this is the unit vector in the PC1 direction. Is that right? So that's a vector of length 1. Now there's a whole circle of directions upon which you could point. So you start from the center, they have the same origin, right? But this guy is PC2 hat. But how do where does the arrowhead land on that circle? There's no information here given for that. Any such arrowhead would be perpendicular to PC1, right? So you need some more rules for determining that. And the rule is the same one that we used before. So how to pick its orientation in the plane, right? So it has to be in the plane. That makes it perpendicular to PC1. But then how do you pick the orientation within that plane? Well, we use the same rule as before, largest variation or variance, right? So you put it down there, project the data onto it, compute the variance, try another one, compute the variance, and so on, until you find the one that has the largest variance. And that's the direction you choose for PC2. Okay, but now remember, this was a three-dimensional problem. So what about PC3? My transformed, my data in this new space has to be described by three axes. So PC3 is perpendicular to both PC1 and PC2. And that, it turns out, is defined up to just a single choice, either positive or negative. And then there's no difference in variation or variance, depending on which you pick. So, in other words, it could point out like this, or it could point out like that. There's no difference. And so you pick one, all right? And then you just move on with your life. All right, so let's talk about the kinds of results you can actually see, right? So results for certain data clouds, for data cloud types. All right, so there's lots of different data clouds you can get. All right, so I have this line barrier here. So let's just say your data lands in a shape that looks something like this. I don't know if it looks like the muffler on a car or something like that. Sort of an elliptical shape, like an elliptical cylinder. Elliptinder? Is there a word? I don't know. There should be. That would be great. So this is like, let's say, so all the data is in there. I guess I can go to green. Why not? So there's the data points. They're like enclosed somehow in that space. Maybe the space is not so smooth like that, but you get the idea that they're in some kind of a shape that could be well encapsulated by this muffler thing, right? And so where would the principal component axes appear here, right? So in this case, the principal component axes would be like this. So you should pause right now and think about it for a second. Where is PC1 in this picture? Maybe it's not even, in fact, I might need to make it more extreme for it to be clear. Yeah, I'm going to have to do that. I'm sorry. I'm going to have to make this longer. Like that. Sorry. Repeat drawing. Okay, and so I'll just put down data points here while you think about it. Like, where is PC1 for this collection? Right? So, in fact, as normal, there's two choices. But you can either point in this direction or out in this direction. right? So just to make my life a little easier, I'm going to point there. And that's PC1. Come on, pen. This is PC1. Right? That's the direction of greatest variation. And the center is somewhere in there. And what about PC2? Right, so I'll draw the center in red while you think about that. So the center is here. So PC2, remember, it has to be perpendicular to PC1. But that doesn't totally determine it. You want to point it in the direction of greatest variation. Right? And so that's going to come out. So this PC1 goes through here like this. PC2 is going to come out like this. And then PC3 will come out like that. Oops. I violated my rules of drawing. Right? Because there's the least amount of spread in that direction. Now, of course, all of these arrows could have been flipped by a sign, and that doesn't change anything. I mean, it might change the numbers, but you don't change the spirit of what it is you've done. And I just have to say, this example, so, suppose the original data set, maybe it, or, in the x coordinate space, maybe the x coordinates were over here. Like maybe this is x, y, and z. And so there's, this little muffler is way off in the side, and, so now we've got it centered and properly oriented. And if we wanted to start throwing out information, maybe the first bit of information we throw out is PC3 and see what happens. Try it out. That's the idea. This is a little ideal, right? Because in this case, it was obvious which way to choose for PC2 and PC3. At least it should have been once you kind of understood how the thing was going. Like it was clear that PC1 should go this way. And then it was clear which direction PC2 should go and so on. That's because of the sort of ellipsoidal shape, right? So let's suppose it was actually, so this is great, right? So great. As you know, that probably never happens. And so let's suppose that instead the data was like this. On a cylinder that was really a cylinder, like a round cylinder, right? Something like that. And so, okay, now, if your data is in this kind of a space, I'll just draw it in blue dots here. Or, and of course, this is fake. This is all fake. Like, in reality, but there's going to be something over here. Like, none of these shapes are going to be really exactly what you see. But this is just as a kind of a mental exercise. So where does PC1 point for this one? I'll just point it the other way just for the heck of it. So PC1 can point this way. The center is here, roughly. And what about PC2 and PC3? Well, here you have a problem, because if you want to make PC2 perpendicular to PC1, that's fine. That makes a plane that's like a cross-section of that cylinder. But where do you point in that plane to get the greatest variance? Like, it's not clear that there would be such a direction, or maybe there is, but it's a small difference. So, so you're going to end up with a PC2 that kind of points off somewhere, but it's not really a useful result, the direction that it came out at, right? Like, so here's PC2. And same for PC3, like PC3 might come out like that. I mean, PC3 is determined once you pick PC2, because it's got to be perpendicular to both of 1 and 2. But, so you see, like, what is the difference between PC2 and PC3 here? Almost none, in terms of capturing the amount of, in terms of the amount of information captured, or the amount of spread in the data captured. So you wouldn't really want to throw out PC3 in favor of PC2. It doesn't seem like that's justified. Okay, so this is not as good, so less great. And then let's go to the disaster. This is meant to be a sphere. I've learned through many ages of drawing spheres that you make it look like a sphere by putting that on it. Okay, so let's suppose the data's in there. Right, and it's spread all over the place in there. Now you're in real trouble because there may not be even a clear direction for PC1. There's no obvious direction of greatest variation. And so you'll get a place, you'll get a location. I don't want to imply that it's somewhere special. So PC1 is going to point there, say. PC2 might come out like that. And PC3 might come out like this. But, that doesn't... what I should have probably done? I should have used like a right-hand rule for determining PC3. Did I manage to do it by accident? I did, actually. That's pretty cool. Never mind about that. But if there's a handedness to how you choose PC3 related to PC2. And I think... Nope, the last one got the wrong handedness. Yeah. To get that right, I'd have to put it... let's fix it, just because I'm ridiculous. So put it there. But again, it doesn't matter. So this one is terrible. So this is bad. Not great, otherwise bad. This is called the problem of sphericity, right? And here's a full sphere. This is one dimension is like circular. And this doesn't have any kind of sphericity, real problems. But anyway, so you get the idea, I hope, of how this kind of can go in 3 dimensions. And of course, like I said, the purpose of this is not to apply it to cases like the one I just described in 2 or 3 dimensions, but we describe it in 2 and 3 dimensions so that we can build up your intuition, okay? Because what we're going to do is apply it to higher cases. So just a remark or comment. These low P examples can generalize. To P much greater than 2 or 3. Too large. And let's just fix my ridiculous spelling there. Sorry. Yeah, so that's just a remark. And I'm going to give you now kind of a spoiler of what's to come, right? So spoiler alert. Right, so this is what we're going to see as we go forward. So it turns out, and this came up in the computational practical, if you guys were there, just as an offhand conversation, it came up. Symmetric matrices. Which we encounter somewhat often. They have orthonormal or orthogonal. They have orthogonal eigenvectors. That is to say, so you have a symmetric matrix, you compute its eigenvectors. Any 2 different eigenvectors will be perpendicular to each other. So that's interesting. Because perpendicularity was a key thing going on in this principal component axis decision making. The covariance matrix which we'll generally call sigma going forward, capital sigma, and I think we called it S in one of the earlier lectures. That's unfortunate. I should have called it sigma. Is symmetric. In case you don't remember what symmetric means, that means that sigma transpose is equal to sigma, right? Or rather, sigma ij is equal to sigma ji. That's what symmetric is for matrices. And so what's going to happen is we're going to use that. So sigma's eigenvectors will point in the direction of our PC axes. They will be our principal component axes. Now, this is the best part. This is really a spoiler. This is all the stuff that we're just going to kind of tell you. It's really amazing. The eigenvalues. So remember, each eigenvector has an eigenvalue, a unique eigenvalue. There may be many different types of vectors that are copies or similar to the original eigenvector that would have the same eigenvalue. But each of the perpendicular eigenvectors for the covariance matrix will have their own eigenvalue. The eigenvalues will be either equal to or nearly so, or representative of the variance. We'll get into the details later. And they will then determine order. Right, so the biggest eigenvalue will turn out to be the eigenvector that goes along with the biggest eigenvalue will turn out to be PC1, and so on. Again, we're going to go over this in more details later. And I just wanted to finish with some natural or physical examples. This stuff that we're doing, it's not really just statistics. It's used in lots of different fields by different names. I don't know that you would hear physicists talk about principal component analysis per se, but the idea, this punchline, this idea of having eigenvectors that determine the principal axes and ordering these axes in such a way that you can decide which things to ignore and so on, that comes up in a lot of different physical examples, and I'll just tell you two that are just, I think, are kind of interesting. So there's something called the inertia tensor. And that can be represented as a symmetric 3x3 matrix in classical physics. And its eigenvalues and its eigenvectors and values really determine the eigenvectors are themselves are called the principal axes of rotation, or principal rotation axes. The inertia tensor describes how difficult it is to rotate a physical object, and the principal axes of rotation rank those difficulties in terms of like most difficult, least to second most, and third most. You'll get three of them in three-dimensional space for a three-dimensional object, so some blob of clay or something like that. So that's an example from physics. The other one, which I guess is also from physics, there is something. I don't know if you're a bio person or a chemist or something like that. Molecules have molecules have something called a polarizability tensor. Or if you want, an electric polarizability tensor. Those describe how difficult is it to electrically polarize a molecule in a particular direction. If you don't know what that means, that's okay. But if you do, then you might find this interesting. And that is also a symmetric, represented as a symmetric 3 by 3 matrix. And its principal, or its eigenvectors, they have a name. They are called the principal polarization directions, or principal directions of polarization. They tell you that if you try to try to electrically polarize a molecule, which means put all of its plus charges kind of on one side and all of its negative charges more towards the other side. So that's polarizing it. If you try to polarize a molecule, this calculation, the polarizability tensor and its eigenvectors tell you the directions along which it's easiest and most difficult to do that. And that's useful for biologists and chemists and I guess sometimes physicists. So that'll be all for this lecture. I hope you feel like you got some kind of an intuition for where we're going with principal component analysis and what kind of things might be coming up in the next lectures. And again, the next lecture after this one will be laying mathematical foundations, and after that we'll start to do some concrete examples. And then we'll start to mix things up a little bit past that. But this is sort of the progression we're going to go on. So I hope you enjoyed that, and I'll see you next time.